This is problem 44 from chapter 17. The uniform bar of mass M is pin connected to the collar which slides along the smooth horizontal rod. If the collar is given a constant acceleration of A, determine the bar's inclination angle. Neglect the collar's mass. So we have three equations that we can use from this problem. We can use the two equations for Newton's second law, and then either this equation here, which is equation 17.7, and this is the equation that we have been using so far in this section, or we can use this equation here, which is equation 17.10. The advantage of using equation 17.10 is that you're summing up the moments about point P, which is not the mass center. But any force that's acting at point P would not appear when you sum up the moments about point P. So in problem 44, you have a force acting at point A, but if you sum up the moments about force A, then that will not appear in your equation, which is good because we're not interested in finding that force. We only want to find the inclination angle theta. So I'm going to choose to use equation 17.10 for this problem, and I'm going to sum up the moments about point A. So I only have one force which is not acting at point A, and that is the force of gravity. So I have the force of gravity acting downwards, and I think here they meant for the entire length of the rod to be L, and if that's true, our force of gravity is acting downwards at a distance of L over 2 from point A. And to find the sum of the moments about point A, we can either take this force of gravity and break it up into components. This angle here is theta, which means this angle here is theta. So if you break the force of gravity down into components, this would be mg cosine theta, and this would be mg sine theta. And when you find the moment for this force, that's R crossed with this force, where R is going from point A to where the force acts. And since you're crossing that with this force here, only this component is non-zero when you do the cross product. So you would have mg sine theta times L over 2, which is the distance from here to here. So if you have your vector R pointing like this, when you do the cross product, this crossed with this component gives you 0. Or when you do the cross product, you could say the magnitude of the cross product is the magnitude of your two vectors, which is mg and L over 2 times the sine of the angle between the two. Okay, so this is the sum of the moments about point A, and that is equal to the sum of the kinetic moments. So for this, we draw a different looking kind of M, so we know it's the kinetic moments. That's what the K is for also, about point A. And to do this, we're going to draw a kinetic diagram for the problem in which we put the mass times the acceleration. And if we had angular acceleration, we would also put the moment of inertia times the angular acceleration, but there is no angular acceleration in this problem. So we put on our kinetic diagram the mass times the acceleration, acting at the center of mass for the bar, which is here. So the collar was given a constant acceleration of A. The bar is also moving with an acceleration A. And then we would do the vector R, which points from A to the mass center, crossed with MA. We could, just like we did here, break MA down into components, and this angle here was theta. So if this angle here is theta, if I draw a line which is perpendicular to the bar, then this angle here is theta also. So I have MA cosine theta acting this way, and MA sine theta acting this way. So when you do the cross product with the vector r and MA, it's only this component, which is not 0 when you do the cross product. So this is equal to MA cosine theta times L over 2. Or if you wanted to do the magnitude of the cross product, you could say MA would be the magnitude of this vector, L over 2 would be the magnitude of this vector, and the angle between the two, since this is theta, this angle is 90 minus theta, but sine of 90 minus theta is the same as cosine theta. Okay, so this equation here, equation 1710, gives us what we have here. Then we can cancel some things out. The L over 2 cancels out. The mass cancels out. If we divide both sides by cosine, then we get tangent theta on the left-hand side. And if we divide both sides by g, we get A over g on the right-hand side. And then to get theta, we just take the inverse tangent of A over g. That's the answer for this problem. And we did not look at Newton's second law here, but if you did want to look at Newton's second law in this problem, that would tell you what the components, the x component and the y component of the force that acts at point A are. But the whole point of doing this was so that we didn't have to worry about that force which is acting at point A. So that concludes problem 44.